So let's try to calculate the scores for the second principal component. Let's shortly call it as it's not writing. Let's shortly call it as PC2 scores. So for that we need the mean centered data, and then we just multiply that x dash multiplied by vector v1 and y dash multiplied by v2, that corresponds to lambda 2. So which means I'm going to write that value here, all this value. Maybe I'll make it like a table now. So 2.2833, 2.6833, 1.8833, so 2.3167, so this, and then 1.1967, this is minus 2.6167, and then so these are the x dash, and then y dash is minus 125, minus 115, minus 130, 120, 160, and 190. So this is something we already calculated before. So what we need to do is we just multiply this with v1 and v2, that corresponds to the PC2, which is this value 0.9998 and then 0.0176. So multiply this with 0.998, 0.998 plus multiplied by 0.998, 0.998. So we are trying to calculate the PC2 scores. And here we should multiply with the v2 value, which is 0.0176, 0.176 multiplied by 176. So what we are trying to do is we're trying to project the mean centered data onto the PC2, or the second principal component, which is nothing but the direction of the second eigenvector. So there's a lot of jargons involved in this type of algorithms, but so there is no other easy method. So that's how it works. So this should be equal to 0.0739. I already calculated the values. So 0.6506 should be equal to minus 4144. This should be equal to minus 0.1957. This should be equal to minus plus 0.9111. This should be equal to minus 1.0258. So these are the final values. Maybe I did a mistake. So I took these two plus 2.2833 minus this value plus minus 125 multiplied by 0.0176. So those are these values. So maybe I should make a third column here, sorry. So for material 1, material 2, material 3, material 4, material 5, and material 6. So the values are 0.0739, 0.6506, and then minus 4144, and this value is minus 0.1957, and then this is plus 0.911 plus minus 1.0258. So these are nothing but the mean centered values. So these values projected onto PC2. So PC2 is something I showed you before already. Where is that data? So we can even draw this one, the values. So we already calculated our PC score, isn't it? Yeah? Minus 1 to 5, something like here. And then you have beside the PC2 score. So and we already know that Earlier I show how the PC1 looks like, somewhere around here. Another one, PC2, is somewhere around here. I already explained how this direction comes from. This is nothing but the eigenvector 2, that corresponds to eigenvalue 2, lambda 2, eigenvector that corresponds to lambda 2, and this is nothing but eigenvector that corresponds to lambda 1. So projected value, what do I mean by that? So the projected values are, so minus 125, 115, minus 130, 120, all these values, isn't it? Yeah? So if you want to project these values on the eigenvector 1, so then you have to rotate this axis. You rotate this axis, and then assume that this is 0, 0, and then you can put these values here somewhere. Yeah? So let's say that this is minus 100, minus 200, and here this is 100, let's say plus 200. So these are the PC1, this is PC1, and if you want to, these are the projected values, isn't it? Yeah? So minus 125, so that will be somewhere around here, and then minus 115 around somewhere around here, and then minus 130, that will be somewhere around here, and then you have 120, that will be somewhere in the right hand side, 160 for material 5, that will be on this side, and then 90, so that will be somewhere on this side. So what we see here, so these are the projected values, so just follow the pen. So these are nothing but M4, M5 and M6, and these are nothing but M1, M2 and M3. So what we see here, we take the we took the two-dimensional data. The original data is you have deliverable capacity and then the operating pressure, isn't it? Yeah? So we took the original data that has a 2 dimension, and then we reduced it into 1 dimension. We projected those values into single direction, isn't it, PC1, and then we managed to identify there exist 2 type of categories. So one is here, which is material 1, 2, 3, and then other one is M4, M5 and M6. So one of this may be viable material good for hydrogen storage, and other class of material may not be good for the hydrogen storage. And this is something we already know, isn't it? Yeah? When we started the problem, I said, so this one you can store at slightly moderate pressure, operating pressure, and it can deliver more material. So these are viable materials. And if you see that, once you implement the principal component analysis, it already categorized the good material from the bad ones. Yeah? So we didn't tell which material belongs to good material, which of the materials can be categorized as a bad material, but nevertheless, once you implement the algorithm, it automatically classifies these 2 different materials. So this is something we can call it as a good class of material, and this one something we can call it as a bad material for hydrogen storage. So this is, and if you see that we managed to do that on a single component, yeah, so that's why we call it PCA as a dimensional reduction technique. Yeah? It's a very good algorithm. Yeah? And then we can do even more with the principal component analysis. So for example, we can even plot. So this is something called as a biplot. So where you can plot PC1 against PC2, and then you can plot the PC score. So biplot is a plot where you plot the PC scores. So since it's a biplot, it has only two axes, which is PC1 and PC2. It's a two-dimensional plot. The name itself tells it's called as a biplot, which and where we plot our PC scores, PC1 versus PC2 score, and we have the, so to do that, so we have the PC1 score. So this is our PC1 score, and we have the PC2 scores. These are the PC2 scores. Yep. And if you want, you can plot these values. So let's plot it. So what I'm going to do is, so minus, I need to plot minus 125 against 0.0739, or maybe I can even make a small table here. So PC1 score is so minus 125.0208 minus 115.0 minus 130.0 minus 120.0 minus plus 120 plus 160.0 and 90.0, and then PC2 score is 0.07 and 0.650, and then minus 0.414, and then minus 0.1957, and then 0.911, and then minus 1.0258. So we can plot PC1 versus PC2. So let's try to do that. So minus 1, let's put this one minus 100, minus, or maybe minus 50, minus 100, 50, 100. And then here we can put like maybe 0.5, 1, minus 0.5, and minus 1. So minus 125 against 0.07. So minus 125 will be somewhere around here. 0.07 will be somewhere around here. So let's call M1. And then minus 115 and 0.650. So minus 115, 0.650 somewhere around here. Sorry, M1 will be 0.07, no? So it will be somewhere in the top. So this will be M2, and then minus 130 somewhere around here, 414 somewhere around here. So this is nothing but M3, and then for M4, M5, M6 is here, no? M120, 160, 90. So this is M4, M5, and M6. So let's plot these values or follow the pen tip. 120 minus 1.17, 120 is around here, minus minus 0.1957 is somewhere around here, M4, and then 160.911, so 160 may be somewhere around here, and then 0.991, it will be around here. So M6, M5, and then you also have 90, and then minus 1.25. 90 will be around here, minus 1 somewhere around here. Yeah? So this is something M6. No, so it already classified the materials when you plot it on a two-dimensional axis, and then we know that our first principal component is somewhere around here, and then our second principal component is somewhere around here. Yeah? So if we can project this component, so this is the direction of the eigenvector, no? And this is the direction of the eigenvector 2. PC2, and this is PC1. So we clearly see some classification of the different materials. And then if we take the PC1 alone, if you go back to the problem which we where we calculated the PC1, let me try to find the paper. So what this value mean? So if you go to the PC1, you have minus some number, and then you have and then you have some positive number which is here. So what does this mean actually? So the 0.9984, if you go back to the original data, so the second coefficient, this talks something about, this talks already something about the something we can call it as pressure, something loading of the pressure maybe. And this number, this is something we can call it as, this is very difficult topic to be honest, yeah, but that's how we have to learn, try to understand, make sense out of the data. And this is something you can correlate to the loading capacity or the deliverable capacity, yeah? So the first coefficient is related to the deliverable capacity V1, and this V2 is related to the operating pressure. So what it means, like, so the loading pressure is positive, and the loading capacity, deliverable capacity, we have a negative coefficient. So what it means is so the PC1 actually, because it's the positive one is on the pressure, isn't it? Yes, the PC1 is something talks about the high pressure. So and then it has some opposite effect on the deliverable capacity. That's why it has a -1. So the PC1, so it if it's more positive, so that means it's operating at a higher pressure. So that's the meaning out of that, yeah. So which means we can call PC1 is essentially which means if you have a higher value, if you have a higher operating pressure, then it means less attractive. And if you have a less or the negative pressure on the principal component, then it means it's more attractive, yeah. So that's the meaning of that. And this is something we already know when we try to plot our values, which is here, isn't it, yeah? So if you see here, not this one, where is our PC1 plot? We already tried to plot here, isn't it, yeah? So whenever you see here, so whenever you have the negative value, which means the large negative value of PC in the PC1, so that means low pressure, which means more attractive material. So that's the meaning of that. So which means M1, M2 and M3, these have negative PC1 scores. On the other hand, the viable materials, which means which in PC1 we know the coefficient V2, that corresponds to high pressure. It has a and M4, M5, M6, the projected value has a positive score. So that's why this can be classified as a non-viable material, because these materials operate at a higher pressure. So that's the meaning of that. I think this should be enough for the moment. And then, and this is something you have to learn by yourself when you try to complete your project. So I already show how this biplot works. So do a bit of research and then try to calculate the direction of your eigenvector, which is typically this one. I already showed you to calculate those values. So this is the direction of PC2 and this is the direction of PC1, and try to plot these arrows, and then you have to explain in your report arrows pointing towards this direction what it means, and the arrows pointing towards this direction what it means. And you see this arrow lies closer to one group of material, which is M3, M2 and M1, and then another arrow which lie closer to these values, isn't it? Yeah? And what's the meaning of that? This is something you have to do a bit of research and explain me. So that should be enough for this topic, PCA algorithm. So I'm just going to summarize, being this so mathematically intensive, because of the nature of the algorithm. So okay, the calculations are very laborious, but time consuming as well. But once you know how to work, then it's really easy. Yeah? So what we did is we took a two-dimensional data, yeah, and then we tried to reduce the dimensions, yeah, and then we tried to reduce it into single component PC1, and then we tried to project the data onto this component, and then we try to show that there exist two categories, yeah, starting from a two-dimensional data, reduce it to one-dimensional data. And the way we project it is to project the data, obviously you need the eigenvector and then the mean centered data, isn't it? Yeah? So x minus x bar comma y minus y bar, and this component, which is something we call it as a one-dimensional component or PC1, this is nothing but the direction of the eigenvector with respect that corresponds to the eigenvalue lambda 1. And we also know if you have two variables, then you can also get two components, and the second component will be typically perpendicular to the first principal component. So that will be nothing but your eigenvector that corresponds to the second eigenvalue, which is your lambda 2. Yeah. The whole idea is to reduce the dimension, and then in the process of reducing the dimension, we capture the entire information. Yeah? So now you see the information is there exist two categories. That's the complete information, isn't it? Yeah? So that's what we did. We tried to project this data onto the first component, and then we show there exist two categories. So in this video, I didn't tell what will happen if we project the data onto the second principal component, which, because we already calculated the projected value, isn't it? Yeah, which is your PC2 scores. If you want, you can plot the PC2 scores, assuming this is 0 comma 0, and then you can plot on this one, but you will see everything overlap on the same point. So which means it gives no information. Yeah? So which is not surprising, as lambda 2 value is only 0.003, which means it carries no information about the actual data set. So whereas your lambda 1 and the corresponding eigenvector, which is this direction, and the projected value on that particular direction, clearly separates category 1 from category 2. So PCA is simply a dimensional reduction technique. Yeah? So you reduce the dimension of the data, without compensating the information in the data, which means you capture all the variance or the entire spread in the data. So that's the meaning of that. Yeah. So try to watch the video, take notes, and then try to solve the problem one time by yourself. First watch the video, take notes, and then try to solve the problem without watching the video. So that's the best way to learn this algorithm, and then you have to solve this same problem in the lab as well. Yeah. So that should be enough for the moment. I will scan all the calculations and then I will upload it in the portal. So thanks for listening.